Hello everybody. Today we're going to discuss about concepts of chemical bonding. And we're going to discuss about the type of bond and the factors that affect bondings at the same time. So when we are discussing about chemical bonding, I would like to start by defining what type of chemical bonds we have. The most common type of bonding is called ionic bond, and then we have covalent bond, and then we have a metallic bond. These are the three types of bondings that we'll be focusing in this slide. Ionic bonds are a result of two different ions. The most common example for ionic bond is if you have a sodium ion, sodium plus 1, and a chloride ion, so that gives you sodium chloride. It's a bond that exists between metallic ion and non-metallic ion. So in our case we have a sodium ion and a chloride ion. It gives you sodium chloride, which is a solid product. And notice here that since you have two different ions, there is a great deal of attraction, and the bond is going to be very strong, and it requires a very great deal amount of energy to break up the bond. Then we have something called a covalent bond. A covalent bond is formed by a formation of two different non-metals or two different metals. Say for example, if you have a bromine molecule, if you have bromine and bromine, it's going to have a diatomic molecule, bromine 2. So the bond between bromine and bromine is going to be a covalent bond. And I can give you another example of a covalent bond. Let's say glucose, is C6H12O6. Okay, it's a bond between carbon, hydrogen, and oxygen. Such type of bond between carbon, hydrogen, and oxygen is going to be also a covalent bond. You have, I can say, nitrogen dioxide. It's a bond between nitrogen and oxygen. Yeah, it's a covalent bond because nitrogen is a non-metal and oxygen is a non-metal. Then the last one that we don't hear often is called a metallic bond. It's a bond that metal atoms bond to several other atoms. So we can have like copper, metal, or iron, or magnesium. It is how the atoms of copper or iron or magnesium are bonded to each other that's going to be a metallic bond. Now the next thing that I would like to discuss with you that the energetics of ionic bonds. So in this case we are going to see what are the factors for creating bonds, the energetics of ionic bonding. So I would like to be a little bit more quantitative in this case. I can give you some example that how is that energetics of ionic bonds can be determined. Let's say let's consider sodium chloride. So experimental result shows that if a sodium atom turns into a sodium ion, and if it lost one electron, it shows that it requires about 495 kilojoules per mole of energy needed to remove electrons from sodium. Okay, so like I say, it also requires, when chlorine ion receives one electron from sodium ion, it becomes chloride minus, and experimental result shows that it releases about 349 kilojoules per mole of energy. So if you think about these numbers, 495 kilojoules per mole for removing sodium ion, a sodium electron from sodium ion, and 349 kilojoules of mole will be emitted or released when chloride ion receives an electron from sodium. But these numbers, obviously, they don't explain why the reaction of sodium metal and chlorine gas to form a sodium chloride will be so exothermic, because when you have a reaction of sodium ion and a chloride ion, and if it forms sodium chloride, the result is supposedly to be exothermic. Exothermic means that energy is released. But if you do the mathematics, 495 kilojoules per mole of energy minus 349 kilojoules per mole of energy, that basically gives you about 146 kilojoules per mole. It's a positive sign. Now, a positive sign is not an indication for exothermic reaction. It's rather endothermic reaction, which is the opposite. So this number doesn't explain you that when sodium reacts with chlorine, the result is exothermic. So we have to find another puzzle. What will be the puzzle that for creating ionic bond? So the puzzle that for creating ionic bond is called a lattice energy. Lattice, I'm going to write lattice energy for you. A lattice energy. First of all, let's define what's a lattice energy. It is the energy required to completely separate one mole of sodium, one mole of solid ionic compound. It can be sodium chloride, it can be potassium chloride, or it can be any ionic compound. So, definition of a lattice energy is how much energy is required to change a mole of a solid ionic compound completely into a gases of ions. So that energy is actually associated with the electrostatic attraction. So this electrostatic attraction is considered our puzzle here. Our puzzle for forming or for bringing sodium ion and chloride ion together to form sodium chloride. So this is a puzzle that form ionic bond, and it's called this attraction, electrostatic attraction, is governed by Coulomb's law, and I'm going to write the formula for Coulomb's law now. So the electrostatic attraction that brings the solid ionic compound together can be calculated as EL. EL is an abbreviation for electrostatic attraction, which has K times Q1 over Q2 divided by distance between them. So Q1 and Q2 is assumed to be the charge of the two ions, the positive and the negative charge, and the distance is going to be the distance between, or the radius between the two particles, and the K is a constant value. So this is a factor that brings the ionic bond together, the attraction between two different ions, and this attraction is also be associated with the lattice energy. The lattice energy and the attraction of the two ions basically are the same. If you just do the calculation, how much energy is needed to release the sodium ion, like I said earlier, like 495 kilojoules per mole, versus how much energy is released when chloride ion gains an electron, which was 349 kilojoules. If you combine this number, you get like 146 kilojoules per mole. This basically doesn't show you that there is an attraction between a sodium ion and a chloride ion. Since if it is an attraction, this number shouldn't be existed. This number should be a negative number. That means it should be exothermic reaction. Because by the definition, every reaction, every ionic reaction has to be exothermic reaction. So the puzzle here is that the electrostatic attraction, which I mentioned here, is the one that plays a significant role for bringing sodium ion and chloride ion. Sodium ion. It's not. I'm just picking sodium and chloride ion, but I'm talking about for all ionic bonds. So one of the things that we need to consider here is that if the charge of the ion is greater, the electrostatic attraction is also greater. Okay, if the distance between the two particles is less, then it implies that the electrostatic attraction is also less. So these are the factors that I want you to pay attention. So if you have a longer or larger distance, which means you have less electrostatic attraction, if the charge of the ion is greater, then you have a higher electrostatic attraction. So to be more practical, we can consider the attraction between potassium chloride versus magnesium chloride. So because magnesium has a charge of +2 compared to potassium, which has a charge of +1, the electrostatic of magnesium chloride has a great electrostatic attraction than potassium chloride. It's because of the charge of the ion. The charge of the ion plays a very significant role here. I want you to pay that attention. Okay, the next thing I would like to discuss is covalent bonds. We discussed about ionic bonds. So when we discussed about covalent bonds, we have a non-polar covalent bonds and a polar covalent bonds. A polar covalent bond. And where does that come from? I would like just to give you an example. Suppose you have, let's start with the example. I have a diatomic molecule with bromine. Okay, if you think about bromine, the way how the electrons are distributed will be the same on each bromine atom. I want you to compare a bromine molecule with hydrochloric acid, for example. Now, here the distribution of electrons is very symmetrical. Okay, and versus with the distribution of electrons is unsymmetrical. I'll tell you what it means. Unsymmetrical means that more electrons are pulled towards the chloride side. I put like a partially negative charge, and there are less electrons on the hydrogen side. I put a partially positive charge here. You can see here an equal distribution of electron. Okay, that's where unsymmetrical and symmetrical comes from. Whereas here there is equal distribution of electrons. Equal distributions of electrons. Okay, so equal distributions of electrons create non-polar because they are the same. You can have a symmetrical distribution of electrons, and unequal distribution of electrons would create a polar covalent bond. That's how polar and non-polar comes from. Actually, where does that idea comes from? That idea comes from there is something called electronegativity. In chemistry, we have electronegativity. Each atoms have they have their own electronegativity values. So what is it? Electronegativity is the ability of atoms in a molecule to attract electrons to themselves. So the more electronegativity that you have, the more electron you will get. So basically here, chlorine has a higher electronegativity than hydrogen does. So there is a big density of population of electrons on the chlorine side than the hydrogen side. So if you do the graph, like here I put like a density of electron on the chlorine side. That means electrons are very much accumulated on the chlorine section, and then there is a deficiency of electrons on the hydrogen side. There is a big amount of electrons on the chlorine side because of the electronegativity value is higher here on a chlorine, whereas on hydrogen it's very less. One thing that I would like to tell you about electronegativity, when you go to the periodic table, the value of electronegativity is increasing from left to right. So it increases from left to right. That means electronegativity increases when you go from metals to non-metals. Alright. Also, electronegativity value decreases as you go from top to bottom. Okay, on a periodic table. By the way, this is called a group in the periodic table. This is called a period. Period in a group. So when you go from left to right, the electronegativity value is getting higher and higher. When you go from top to bottom, the electronegativity value is going to be down or decreased. So you need to, in order to understand this concept, you need to have a periodic table in front of you, and it gives you a clear picture of about the value of electronegativity. And just for your information, an element fluorine has a higher electronegativity, and its value is about 4.0. It's measured quantitatively, and it provides you about 4.0. That's the highest one. This is the maximum electronegativity value you can ever found in a periodic table. So one thing about, I would like to add one point about a polar covalent bond. Since we are discussing about unequal and equal distributions of electrons. If you have a polar covalent bond, which means if the electrons are shared unequally, what happens is there is something called a bond dipole result. So let's say that you have a charge of an ion with a Q plus, and you have another charge of an ion with Q minus, which this guy has a high density of electron here, a high density of electrons here, and this guy has a low density of electron here, low density of electrons here. A bond dipole, this is a distance between the two. A bond dipole results, and in chemistry we call this dipole moment, and the dipole moment is represented by a Greek letter mu. It is a product of two equal but opposite charges, which is separated by a distance r. Instead of d, I would prefer to use r. I'm sorry. I mean, some literatures they use d, or some literature they use r. So the dipole moment mu is the product of q times d, or if you like, it's mu times q. Mu equals to q times r. And the dipole moment is measured in a unit called debye. So you may see a letter, capital letter D, debye, which represents D. It's a unit for measuring a dipole moment. Now remember that dipole moment always comes from unequal distributions of electrons. And you may experience this from polar covalent bond, unequal distributions of electrons, and from polar covalent bonds. If you have a non-polar covalent bonds, you may not see any dipole moment at all. So we're going to complete this video for right now, and we're going to continue the next part of chapter 8 in the next video. Please share this video and like us and share to your friends, and I'll be very happy. I'm very grateful if you write your own comments on the videos that can be improved, and that how we can do better to serve you. I appreciate that, and shortly I'm going to have the next video that will be a continuation of bonding.